Go ahead.
Okay, hello everyone. I'm Balint. Welcome to our first advanced lecture. So today I will maybe go slightly faster than yesterday, but I will obviously still try to explain everything nicely. So today's lecture will be about square root decomposition and segment trees. So yesterday we covered prefix sum arrays, where we made a data structure that computes the sum of every prefix, and that allowed us to answer range sum queries, where we were given an array and we wanted to find sums of different subarrays of that array. Now, prefix sum arrays were pretty nice. You constructed them in O of n time, and after that you were able to do queries in constant time. And the way they work is you compute all the prefixes, and you can take the difference of two prefixes to find the sum of an arbitrary subarray. And this worked because addition is an invertible function. So basically, if we know like the sum of the first two elements, we can just negate them and then do subtraction to find the sum of this range, for example. However, there are some things prefix sum arrays cannot do. For example, consider this problem. You are given an array A of n non-negative integers, and you have to process q queries, and the queries can be of the form given indices L and R, output the maximum value of the elements of the array with indices from L to R, or given an index P and the value V, set A of P equal to V. So this is like a query operation, and this is an update operation. And you will notice that prefix sum arrays really cannot support either of these operations. Updates on a prefix sum array would be expensive because you might have to update all of the elements of the prefix sum array. For example, if you update the first element of the original array. And then prefix sum arrays also just like fundamentally do not support range max queries. Like if we try to make a prefix maximum array, for example, where we store the maximum of every prefix, we can't really just use those values in a useful way to like find the maximum value of an arbitrary subarray, because like max is not invertible. Like for example, I mean like a trivial way to think about it is, what if the first element was the maximum value? Then all the values in our prefix max array would be the same, so then it stores like almost no information. So the prefix max array just doesn't work at all. So we need to find a different way to approach this problem. So first, we will focus on how to do queries efficiently. And once we have done that, then we will focus more on updates. Okay, so let's say, as you remember, the constraints in the problem were like number of queries and number of elements in the array are both up to 200,000. So let's say we have, and then just the brute force solution is obviously too slow, because to do a query you might have to iterate through the entire array, which would be 200,000 operations, and if you do that 200,000 times, that's like 4 times 10 to the 10 operations. That's quite slow. However, it's not that slow. It might be kind of close to the time limit if you're using a fast language like C++. So what can we do to make this just a bit faster, to just like save some amount of time on our computations? Well, one thing we could do is we can split the array into blocks. Since like every time we're querying like a consecutive range, there are like a lot of ranges that we query many times, kind of. So for example, let's say our size 200,000 array, we split into blocks of size 100, and each block corresponds to like a different subarray of our array, and in the block we store the maximum of that subarray. We just pre-compute this at the start before doing any queries. In this case, all of our queries would basically be a factor of 100 times faster, because for like most of the range, we would just be iterating through the different blocks. And at that point, we're basically doing like 100 elements by only looking at a single value. Of course, the exception to this is like the parts at the start, or the end and at the start that are like hanging out that in from the blocks that like aren't fully contained in a block. So the total amount of time we spend with this approach is so let's say our blocks have size b. Then in each query there will be at most b minus 1 items on the left that are not like fully contained in a block, b minus 1 items on the right that are not fully contained in a block, and at most n over b blocks. And we just iterate through all of these, take the max of all of those values to get the final answer. And then if we set b equal to square root of n, then the overall time complexity will be square root of n for the elements on the left, n over square root of n for the blocks, and square root of n for the elements on the right. And this is just 3 times square root of n, which is still all of square root of n. So does anyone have any questions about how this strategy works? Just for queries. I will cover updates in a second. No? Everyone understands how this works? Okay, cool. Okay, so now let's think a bit about updates. So let's say we started with our array, we pre-computed the blocks, maybe we did some queries, but now we have an update. We want to change this 20 in our original array to a 5. So to maintain like the validity of our data structure, we will also have to recompute the value stored in the one block that contains this element. So the way we do that is very simple. We just like brute force recalculate the value of that block by just looping through all of the elements in the array, taking the max of them, and assigning that to the value of the block. So this will take O of b time if we are using blocks of size b, and if we set b equal to square root of n, this also takes O of square root of n time. And then obviously, if we are changing only this value in the array, that doesn't affect like the other blocks at all, only this one. So we don't have to do anything else. Okay, so right now we have an algorithm that solves the problem at the start where we want to do range max queries, and we also want to support point updates where we update a single element in the array. And currently we can do queries in square root of n time, updates in square root of n time. Our pre-computationist time is linear because we basically just iterate through the entire array to compute each of the blocks. And our space complexity is also linear, and in reality most of that just comes from storing the initial array because the number of blocks is a lot smaller. So this solves our problem in O of n plus q square root n time, and that's already pretty good. Q and n are both 2 times 10 to the 5, so this is probably already good enough to pass. However, okay, so does anyone have any questions about this approach? Okay, so however, can we do better? The answer is yes, and because of that, I will not go into details about how to implement square root decomposition, because it is quite rare that you actually implement square root decomposition, because the idea I will present next is usually also works for mostly the same set of problems and is faster. Okay, so let's go back to the case where instead of setting the block size to be square root of n, we just set the block size to 100, and our original array size is 200,000. You will notice that like most of the time, okay, let's break down how much time we spend on each part of our algorithm when doing a query with these parameters. So we spend like about 100 operations on the left, 100 operations on the right, and then 20,000 operations querying these blocks. So most of our time is spent doing a range maximum query on the pre-computed blocks. Correct. So does anyone have an idea of how we could make this faster other than just by changing the parameters? Yes?
Pre-computed blocks for each blocks.
Well, yes, exactly. This is kind of a recursive problem. We came up with a data structure that can do a range maximum query efficiently. However, it has a sub-problem that is also just do a range maximum query. So why don't we apply the same idea again and just pre-compute blocks for this layer? When we do that, you will notice we could get like O of cube root of n time complexity for updates and queries. However, again, a lot of the time will be spent just doing a range max query on the top layer of blocks. So we just compute blocks for that as well. And this leads us to the idea of segment trees, where we just do do this like blocking idea repeatedly until we get down to a block of size 1. So a natural question to ask is what block size should we pick at each layer? Now, the most common answer to that is we pick 2 because, well, so if we pick blocks of size 1, obviously it will not work because then we don't like reduce the number of blocks ever and we would just need to have an infinite number of layers. And like 2 is usually a pretty convenient number to work with. And that also means that like on each layer we won't have to do a lot of work because the number of elements that will not fit in a layer on the next block on both the left and the right is just 1. So on each layer, when doing a query, we will only be doing O of 1 work by looking at only 2 different values. So that's very good. Now, the other thing to think about is how many layers will we have? So on each layer, we have the number of blocks because we are always taking like 2 adjacent values and basically merging them into one block. So in total, we will have log base 2 of n layers. So that's pretty good because log n is a small number. Okay, yes. So let's think a bit about the queries and the updates on just like a high level. So on each query, we only have to look at on each query, we only have to look at 2 values on each layer, because if we're thinking about it from the perspective of like repeated block decomposition, we will only have like one thing that doesn't fit in the block on the next layer on the left, and one element that doesn't fit on the block, like the next layer's block. So since there are log n layers, and we look at most 2 values on each time, we have to look at most 2 times log base 2 of n nodes in total. And then for the updates, each update will only like affect the values that are directly above it in this diagram. So that will again be only log base 2 of n values because each block only has like one parent, like one other block above it. And those are the only values we have to update. So we have to update only log base 2 of n values. So that's also quite good. And then we will show how to do all of these updates in each update in a O of 1 time. Okay. So another detail we will try to make. So now we have like the general idea of a segment tree. Now let's try to work out a bit more of the details of how to actually do all of these operations. So the first thing is we want to make sure that the input array, the size of the input array is always a power of 2, because like at every layer we have the number of blocks. So if at some point the number of blocks is not even, then we cannot have it nicely. So generally, it is just most convenient to just have the array to a size that's a power of 2. For example, by just putting in dummy 0 values or something. And then another thing that's important to think about when understanding segment trees is that every value in this data structure corresponds to the maximum of some subarray. Okay, so for example, if you have this value or segment or whatever we want to call it here, it will correspond to the max of these 4 elements in our original array. And that's true of like every value in that tree or in our data structure. It corresponds to the max of some subarray. And you will, if you pay a bit of attention to this structure, you will also notice that it forms kind of a binary tree structure. So for like each node or like block has 2 child blocks that are like contained within it, and 1 parent block that is like above it. So this is exactly a binary tree structure, if you have heard of that before. And then this is where the name segment tree comes from, because you have a binary tree where every node corresponds to some segment in the array. And I guess another concept that's somewhat useful to think about are the different layers. So you have like the bottom layer here, and everything on the bottom layer is kind of similar. Everything here represents an subarray of size length 1, and then everything on the next layer represents a subarray of length 2, and so on. Okay, so that is basically how we define a segment tree and like the high-level idea. Now let's look at how to do the actual operations. Does anyone have any questions so far about how we roughly define our data structure? No? Okay. So let's start with how to build the segment tree from the array. So let's say you're just given the array and you want to initially just construct the segment tree. So the way you do that is first you copy the array into the last layer of the segment tree, because everything here represents a subarray of length 1, which is just a single value. And then once you have all of those values, you can compute the layer above it. And once you have all of those values, you can compute the layer above it, and so on. And the fundamental reason this works is because once we know the value of 2 blocks, we can also compute the value of its parent block in O of 1 time by just taking the maximum of the values of these 2 blocks. And like the reason for that is like this block represents the maximum of this subarray of length 2. This block represents the maximum of this subarray of length 2. So then if you just take the maximum of these 2 values, you get the maximum of the entire subarray of length 4, which is exactly its parent. So this is like a very important concept for segment trees. If you know the values of like 2 adjacent blocks that have a common parent, then you can use those 2 values to compute the value of their parent block in O of 1 time. Does that make sense? Okay. Okay. Now, as for the queries, the way we will do the queries is we will just pick the minimum number of segments in the tree that cover the entire subarray and take the max of those segments. And this results in taking up most 2 segments in each layer. Again, based on like the intuition from the repeated square root decomposition, because there's only like 1 value that's not fully covered on the one value on the right and one value on the left that's not fully covered by a block above it. So this results us in taking 2 times log n segments. I will explain the procedure for how to find these segments in a second. And then yes, so for the updates, one way to think about the updates is we can start at the bottom. So let's say this is our initial array. This is our initial array. This is the segment tree that we have already built. And now we want to update this 9 to a 3. So the way we will do that is first we will change the corresponding value in the segment tree. And after that, we notice that we might have to recalculate the value of the parent of that block because it has changed. However, we can do that in all of one time by just taking the max of these 2 blocks because we have already computed those. But again, we notice we changed this value, so we might have to change the value of its parent as well. But again, we just do that in all of one time by taking the maximum of those 2 adjacent blocks and so on until we get to the top of the segment tree, the root node. And so as I said, there are log-based 2 layers, and like on each layer, I only had to change one value, and I was able to recompute that in a constant time by taking the maximum of its 2 children. So every update will take log n time. Okay, so now let's move on to the actual implementation. So far, I gave you most of the concepts of how a segment tree works, but like I didn't really yet explain how you can actually write code to do all of these operations. So the first thing is we will represent our segment tree as in an array. So for like other tree structures, you might want to store pointers to the children and pointers to the parent. However, that is and you could do that for segment tree as well, and that would work. However, that like takes up a lot of memory and that's computationally expensive. So what we do instead is we use the fact that segment trees have a reasonably nice and consistent structure to try to embed them in an array. So the way we do that is we give like an index to each of the nodes. We give the root node, which corresponds to like the entire array, an index of 1. And then we say that the children of a node with index I will be stored at locations with indices I times 2 and I times 2 plus 1. And then by this, we also know that if we know the index of a node to get the index of its parent node, we just divide I by 2 and take the floor of that. And that works because like I times 2 divided by 2 is just I, and then I times 2 plus 1 divided by 2 is I plus half, the floor of that is just I. Okay. And you will also notice that this indexing doesn't really cause any collisions. Like it will never, because like the parent of each node is unique, and you know exactly where its 2 children are, there will never be like any kind of ambiguity. And this will map all of the nodes of our tree to different indices in the array. So one other nice property of this representation is that all of the layers will be consecutive. So in our data structure, index 0 is, we just kind of ignore that, we don't use that ever. Index 1 is the root. Indices 2 and 3 will be the left child and the right child of the root. And then the next 4 indices will correspond to the next layer of the segment tree. And then the next 8 indices will correspond to the layer of the segment tree after that, and so on. So you will see in a second that the fact that the layers are ordered like this is quite convenient for implementation. Any questions about how we store the segment tree? No? Okay. So then I guess the other thing to note, So let's say the bottom layer has length n, and n is a power of 2. Then the total size of the segment tree will be like n plus n over 2 plus n over 4 and so on. And this is just a geometric series, and the sum of that is 2n. So in total, we will use 2n space, where n is like the size of the array, but like rounded up to a power of 2. So let's look at how to implement the construction of the segment tree. So for the example problem I gave earlier, where the size of the array is at most 2 times 10 to the 5, then we would have to make the size of our segment tree at least 2 to the 18, because 2 to the 18 is equal to 262,144, I believe, and that's the smallest power of 2 that's greater than 200,000. So in these implementations, I just hard-coded those values. I guess you could also have something that takes like the length of the array, takes the log base 2 of that to calculate the power of 2, not too important. And then so the main array, throughout my implementations in which I will store my segment tree, I will just call tree. I initialize that with all zeros. And then for my build function, all I do is I copy the array into the last layer of the segment tree. So that would be like, here's the array, I copy to the last layer of the segment tree. And then after that, I just iterate through all of the remaining indices, and I calculate them based on the values of its 2 children. So as I said, I times 2 we define to be the left child of each index I, and I times 2 plus 1 is the right child. So this line of code right here basically does the operation I showed earlier, where you like, for example, set the 8 to be the max of its 2 children. Any questions? Oh, wait. Okay. So now let's look at queries. So for queries, we will implement queries using our recursive function. There is also an iterative implementation of segment trees that has some advantages, which I will not cover during this lecture. But anyways, the way I will do the queries is I will have a recursive function that takes in some information that identifies the segment. I will go into a bit more detail about that a bit later. And then 2 values, L and R, and it will return the max value of the intersection of this segment, which is like one node in our segment tree that corresponds to one specific subarray. And it will return the max of the intersection of the segment and the range L to R. So, for example, if this is the segment that is passed into the query function that corresponds to this subarray, then it will return the intersection of this range, like the max of the intersection of that range, and the range represented by L and R, which is just these highlighted dark green values, and so it will return 7. So generally, when you are making a recursive function, it is important that you make your definition very precise so that you can argue about it nicely when actually trying to do any kind of recursion. Right. So now you might wonder, why did I define my query function this way? And one reason for this is that if I just call the query function on the root with a range L to R, it will simply return the max of all elements between L and R, because the root contains like all of the elements on the array. And then also it's just because defining the query function this way makes it actually possible to do the recursion. So, there are three different cases for what you might have to do in the query function. So the first thing you might have to do is, let's say the segment is completely contained in the range L to R. So here I have two different examples of how this might look like. Maybe like L is very far to the left of the segment, R is very far to the right of the segment, or maybe they're exactly on the segment, it doesn't really matter. If the segment is fully contained in the range L to R, then I simply return the value stored at the segment. And this is because we define the value stored at the segment to be the maximum of its subarray, and that's exactly what we want, because in this case the intersection of the segment and L to R is like exactly the segment's range. Now the second case is what if the segment is completely outside of the range L to R, there's no intersection. So I again have two examples. Maybe it could be very far to the left of L to R, or it could be to the right of L to R. Doesn't really matter. In that case, I just return 0 because the tubes, like the segment and the interval, don't have any intersection. So I have to return a value that basically represents nothing. And in this case, for the max function specifically, maxing a non-negative integer by 0 does nothing. So that is what I return. And then the third case is, what if the intersection is more complicated? Maybe L to R is contained in the segment, or maybe L to R has like some partial overlap with the segment. That is really quite complicated. So in that case, I just recursively call the query function on the two children of my segment, and I return the max of the those two values. And like this is where it's important to think about how I define my query function, because I define my query function to be like the max of the intersection of one segment and the range. And then if I do this, this will work exactly, because like I will compute the max of the first half of my segment, which is the left child, intersected with my range, and the right half of the segment intersected with the L to R, which is the second half of my range, and then I combine those. That will just get me this segment intersected with L to R and the max of that. Okay, does anyone have any questions about how the query function works? Yes?
Can you explain what L child and R child are?
Okay, yes, I did not, sorry about that. Yes, so I did not define those yet, but those are basically like the two blocks below the segment. So for example, for this 7, if we treat this as like a node in a binary tree, then it will have two children, which are these two nodes. So just like the two blocks directly below it. So for the actual code, the way I will access those is mostly by saying like I times 2 and I times 2 plus 1. But they're basically like the two blocks that combine, two smaller blocks that combine to form the bigger block. Okay, that makes sense? Okay. Any other questions? No? Okay. Okay, sure. So let's go through an example of how this recursive function might play out. So let's say this is our segment tree. The bottom row is our array, because that's just copied. And we are interested in the maximum of that range. So we would call the query function on the root. We notice that it has a complex intersection, so we recurse on its two children. First, let's try to evaluate the intersection of L to R with 9. We again notice that the intersection of that is still reasonably complicated, so we again recurse. But this time, the 8 is fully outside, this segment is fully outside of L to R, and this segment is fully inside L to R. So for both of those, we know what to do. we just return 0 for the left segment, 9 for the other one. And then when the recursive function for this segment returns, it will just take the max of these two, and that's 9. And you can verify that that is correct. That is in fact the max of the intersection of that segment and L2R, which would just be this range. Okay, on the right side, the 14 still has a complex intersection, so we recurse. The 14 on the left, however, this segment has like a simple intersection because this is fully contained in L2R, so we just return 14. And then for the 13, we keep recursing because it's still complicated. And at this point, the 6 is fully contained in our range, the 13 is fully outside of it, so we again know what to return. And then as our recursive functions return, they basically successively just take the maximum of all of the red values so far. So that 14 will return, that will take the max of those two. And then the top 14 will return, which will take the max of those two, which is, in fact, the maximum of the range we were interested in. Okay. Okay, so far I kind of just had like a mystery parameter segment that I didn't really explain how that would work. Now, but the actual values you care, the actual like properties of a segment you care about are its index, which I represent with the variable I, and the left and the right endpoint of the segment. So, for example, I equals 1 means that this segment is the root node, I equals 2 is the left child of the root node, I equals 3 is the right child of the root node, and so on. This works according to the definition I had earlier, where the children of a node are like I times 2 and I times 2 plus 1. And then the other important information we care about are like the left and the right endpoints of the segment. So that basically means that the value of like the segment that's like 3 of I is the max of the elements in the original array that have indices in the half inclusive range seg L to seg R. So in my actual implementations, I try to make all of my ranges half inclusive on the left and exclusive on the right, even though that might not be what I did in some of the diagrams earlier, because I think those are generally quite nice to work with. So for example, if to my query function I pass the value seg L equals 2 and seg R equals 4, then what that represents is that the value of this segment, which is 3 of I, is equal to max of R of 2 and R of 3, because 2 and 3 are like the only values in the half open range 2, 4. And then L and R are like the actual query parameters of like the range I'm interested in. Okay. Wait, do I not? Sad. Okay. So for updating an element, the way that will work is I will again I will want to change the like all of the segment, all of the values on all the segments that are directly above this. Now updates are actually reasonably simple to implement iteratively. However, those can also be implemented recursively. And I will cover the recursive implementation now. It's very similar to the query implementation. So basically the parameters will again be a segment, some index, I should call that something else maybe, but let's call it I, and the amount that I want to change it to. So the way I define this function is that I want to update the value of this segment and all of the segments below it, and I am changing the value of the array at index I to the value amount. Huh? Okay. So there are two main cases for this. One case is that the segment contains the element. So in this case, and then the other case is the segment does not contain the element. So if the segment contains the element, then I will just recursively update the two children and then recalculate the value of this node. Now in reality there is another third case that's kind of a subcase of this that I didn't really put on the slide, which is what happens if the segment has length 1. If the segment has length 1, then I just directly override this value and I don't update any children because there are no children. And then if the segment does not contain the element, then I just do nothing. So like this implementation will work. It won't do too much extra work because on every layer, whenever it tries to recurse on a segment that doesn't contain the element, it will just return instantly. So the only blocks it actually recurses on are the ones that are directly above the final value it is going to. Okay, so here is the actual code. I think maybe I should have put the query code after explaining what the query stuff, but whatever. So here's the query function. It takes in the parameters I, segal, segar, lr, and first it tries to determine like which case it is in. So if the L and R and segal, segar ranges are completely disjoint, then I do nothing. Then I just return 0, basically like do nothing, because in that case there is no overlap. However, if L to R like fully contains segal to segar, so basically like the query range fully contains the segment, then I just return the value stored of the segment, and otherwise I recurse on the two children. So one important thing to know is that I have to compute the midpoint of these segments to be able to like actually make the recursive calls. So fortunately, the way I defined my half-open intervals, this is actually a very nice operation. I straight up can just calculate the average of the segal and segar, and that will be the right endpoint of the left child and the left endpoint of the right child. Right, so this is how I do queries. So like the left child will have index I times 2 because that's how I defined it. The left child will start at index segal, obviously because it has to like, it will be aligned. Like it starts at the same position as this one, and then it will end at the midpoint. And then for the right child, it's kind of similar. The index is I times 2 plus 1. The starting point is the midpoint of the segment, and the ending point is just the ending point of the segment. And then the update function is, the code is very similar, except this time I'm not passing it a range, just a single point, which is an index, and then a value. And then at each like recursive call, I check if the value is outside of the range, in which case I do nothing. So I think in this specific implementation, I do return a value because here I just say that I want to always return the value that's actually computed. And then if the segment has length 1, then I again just update it, and otherwise I just recurse on the two children. Okay. And then the C++ code is very similar, just the syntax is slightly different. Okay. Does anyone have questions about the implementation, or should I maybe like leave it on the board for a few more seconds for you to look at it? Or is there a specific part I should try to explain a bit more? Okay. So the kind of problems we have been able to solve so far are like range query problems where an update requires you to modify a specific element of the array, and the query requires you to compute some function evaluated over elements of the array, of a subarray. And with a segment tree, these operations can be done efficiently in OAuth log and time, both queries and updates. Now, a segment tree, fortunately, is a lot more general than a prefix sum array because there are a lot fewer requirements on what functions it supports. So really, the only property that a function must satisfy is it has to be associative. So that basically means that you can rearrange parentheses in an expression involving the function however you want. So for example, if our operator is just star, where like star could be, for example, addition or like max. I guess for like max you write the notation slightly differently as a function, but it's still like a binary operator. That is like the proper like equation it has to satisfy. So you will notice that, for example, max satisfies that, addition satisfies that, XOR satisfies that, and lots of things satisfy it. So that makes segment tree and also square root decomposition a lot more general than prefix sum array, where we had the additional requirement that the function needs to be invertible to like do the subtraction kind of thing. And I guess the other requirement is that if like the star is the function or operator you are evaluating over the subarray, then calculating A star B should be fast, usually constant time. Because you can imagine maybe if the values you're dealing with become huge, then even if the function is associative, a segment tree might not be too good. Okay, any questions so far? Okay, so I have spent about 50 minutes so far. I still have another section about range updates that I could cover. However, maybe this is already enough content for today. Can I have a vote? Okay, first, let's say I could probably cover it in like 20-ish minutes. So then we would go over like the start time of our problem solving session. Raise your hand if you want me to cover how to do range updates as well. Okay, that's actually quite a lot. Okay, and raise your hand if you think that we already did enough for today and we should just get started with the problem solving session. Okay, that's a lot fewer hands. Okay, in that case, I will cover how to do range updates as well, and obviously we will go a bit over time, but that's fine because we have the problem solving session. Okay, so far our segment tree and square root decomposition can only support updating a single value. However, what if we have a different problem where we want to update an entire range of values in the array? So let's say the operations we want to support are increase every value in the range L to R by X, where L and R and X are just given in the input. And then we want to find the max element in the range L to R. That's the same as what we were doing before. And then again, the constraints are also still the same as what they were before. Maybe the length of the array is about 2 times 10 to the 5, and the number of queries is 2 times 10 to the 5. So brute force will be O of NQ, which is too slow as usual. And we again want something whose time complexity is maybe like Q log n or Q square root n or something like that. So the fundamental issue is if we update a range, that might affect a lot of the values in the segment tree. Specifically, if we have a range that covers almost the entire array that would affect like almost all the values in the segment tree. So you would have to recalculate all of those. So that's bad. Because there are like O of n values in a segment tree, so an update would take O of n time, which is slow. So that might mean. So sadly, does that mean? Okay. Also, the contest is apparently open if people want to submit to that. But like, just listen to my presentation would be nice. Okay, so you might think, oh no, we are screwed. Our segment tree approach will not work anymore at all. We have to get a new idea. However, that is not really true. Our segment tree can be we can make a small modification to it to allow updates.
Recording stopped.
Recording has been stopped for the Zoom meeting.
Oh no.
Yeah, someone fixed that. We have like the record. Wait, Mo. Can I just keep going? Okay. So, if there is one thing I learned from 65210 advanced algorithms, which I guess is after I learned segment tree, but like small detail, is that when doing a data structure problem, you should be as lazy as possible. Don't do any work that you don't have to. So, that leads us to the idea of a lazy propagated segment tree, where instead of updating like all of these blue values that are highlighted, we won't update all of them, only the ones that are like, that kind of matter in some sense. So the way we will achieve this is at every node in our data structure, we will store a second value, which we call its lazy value. And what that will represent is that if a node has a non-zero lazy value, so for this specific operation, what that will mean is that every element in the subarray corresponding to that segment has been increased by that lazy value. However, the segments in the subtree of that segment have not yet been updated to reflect those changes. So what I mean by that is, for example, let's say we start with this array, and then we want to increase all of these values by 5. Then what we might do is we might give this segment a lazy value of 5, and then also recompute the actual value of this segment and its parent. But we do not do any computations on this entire subtree, and we instead just store this lazy value, because that will represent the fact that all of these values still need to be increased by 5. Well, okay, more specifically, it represents the fact that this entire range has been updated by 5, so we have to do something to correct these values. However, those corrections have not yet been made. So what that means is that these two segment trees here represent the same array, but just stored a bit differently. Okay, does that make sense? And okay, I guess maybe to my definition, so what the lazy value represents is that everything in the subtree of the node, which is everything below it, has not been updated, but that excludes this node because this node has had its normal value updated as well. Okay, questions? No? Okay. So the reason this is useful is because now we can do updates more efficiently. So if we consider the same update from earlier, we will not have to update all of the values that were highlighted earlier, only these ones. Because if we look at all of these things, all of these nodes, they are already fully covered by a different segment. So we could instead just assign these a lazy value, and then we have to do fewer computations. Specifically, what will happen is for the yellow nodes, we will kind of like fully update them and like fully do a recursion thing. But then for the blue nodes, we will notice that those are fully contained in our interval L to R. So we will stop the recursion there and instead just put a lazy value beside them. Okay, and then the idea is that these lazy values are okay because with our recursive query implementation, I claim that it is possible to like expand or propagate the lazy values when we actually need them to do a query. Okay. So basically, how all of our recursive functions will work is whenever we have a recursive function that tries to do anything on a segment, one of the first things it will do is it will just propagate its lazy value downwards, so that when we try to recurse on its children, the value stored there will also be correct. So, for example, if this is the current segment, it represents a range of, doesn't really matter, length 4, length 8, I don't know how big I made this. And these are its two children. And this is a lazy value of 11. What that means is that all of the values in the array have been increased by 11. And now for max specifically, this can be propagated efficiently. Because for this segment, I know that it represents some array such that the maximum value in that array is 12. And then it receives an update that increases all of the values by 11. So maybe the array it represents is, I don't know, like 4, 12, 7, 3. If I increase all of these by 11, then I know that the max is also got increased by 11, right? Because the 11 was applied to the entire segment. So then I know that the new value for this node, when I expand the lazy value, is 23. And then of course, same thing for the right side. If initially the max was 27, and I update every element in the segment in like the subarray corresponding to this segment by 11, then the max of that segment also increases by exactly 11. So I just do 27 plus 11 equals 38. And then once I have propagated these, I will set the lazy value of the current segment or the parent segment to 0 because that has been propagated down. However, I have to set the lazy value of these segments. I increase those by 11 because now I know that like everything that would be in the subtree of those has not really like received the update of 11 yet. And then this also takes constant time. Any questions? Okay. Okay. Do I not even have a Python implementation for this? I see. Okay. So the build function is the same as before. Don't worry about that. You copy the array and then you do the merging. I don't think I have the array copying here. But then the important thing is now we will have this pushdown function. In this case, the only parameter it takes in is the index I of the segment. For some other operations, you might also want to pass in seg_l and seg_r into the pushdown function. But this pushdown function does basically what I described in this slide, where it takes a single segment as its parameter and it expands the lazy value to its two children. So the way I do that is, I actually just incremental of these values by the lazy value of the current segment. Because for the specific operations I'm doing right now, which is like the updates are adding v to every element in the range and the queries are getting the max in a range, that is what you have to do as I explained. You just increase all 4 of these values by 11, or like whatever used to be stored here. Okay, the query function is identical to what it was before, except now we have a push down call. That's not correct. We have a push down call in the middle, and the update function was changed a bit, but the update function now looks extremely similar to the query function. It also takes in a segment, the endpoints of the segment, and the endpoints of a range. And the recursion you do for the update function is very similar to the recursion you had to do before. So the 3 cases are the same. You have one case of what happens if the range is completely like disjoint from the segment, in which case I don't do anything, I just return a value, I don't update anything. And then probably the most interesting case where stuff actually happens is if the range is fully contained, if the segment is fully contained in the range we want to update. In which case I increase the lazy value and the segment tree value. And if neither of those are the case, I just recurse on the 2 children. And then I also recalculate the value of this tree. And then before that, I of course call the pushdown function. Okay. Oh, okay. This exists now? Yay. Okay. So that is what we had for today. You should probably try to implement the non-lazy segment tree first for our problem sets. And once you have a good understanding of that, then you can try thinking about the lazy segment tree with the range updates. Any questions? Okay. Thank you for listening to my presentation today. I think tomorrow we will have a beginner lecture by Wei Ming about trees and other operations you can do on them. Okay, thank you.